So here I'm here to talk to you about ZFS with MySQL. So here's the talk. So who am I? So I'm a principal architect at Percona. I joined Percona in 2009. It has been already 10 years. Prior to Percona, I've been working with some microsystem and MySQL AB. So I've been around MySQL for most of the last 12 years. I'm a physicist by training, so I like to understand how things work. So, why a talk on MySQL and ZFS? The simplest explanation is because I like both and I'm undecided. So I decided to mix. And they go along very well in many cases. So how many here have touched ZFS in the past? Oh, it's quite a nice crowd. Okay, very good. So they share many points in common, so which is also very interesting. So my plan, I'll do a quick tour of ZFS. Many of you already know, so it will be rather good. I'll set some configuration guidelines for MySQL and ZFS to work well together. And I'll give some real-world examples using cloud-based configurations. So a tour of ZFS. So let's give some highlights on ZFS. So it has been developed by Sun for Solaris. I think it's around 2004, 2005 that the first release were made available. It's now in many platforms. I mean, I think there's, of course, Linux, BSD was there before, Illumos, Mac OS X has it. So, whoops. What's special about ZFS is that everything is stored in a B tree. While many file systems like XFS and ext4 will store the directories in B trees, they will not store the files, the content of the file in a B tree. ZFS does. The files are fragments that are stored as leaves of a B tree. One thing crazy about ZFS, it uses 128 bits pointers. You have to realize that 64 bits give you 16 exabyte. Have you ever seen a file system of 1 exabyte? I've never done. On a single physical server, it's like crazy, but ZFS can do that square, so much larger. Files are split, like I said, in records that are the leaves of the B tree. A server, the records are entities that can be compressed. There's many algorithms you can use for compression. Some are faster than others, we'll see. ZFS uses a principle of copy and write. We'll cover that a bit later. It has now, with the latest versions, native encryptions. I'm not sure if it's GA yet, but you can easily compile it if you want it. Checksums and self-healing. Every record has a checksum. And since in many configurations we'll use mirrors or multiple copies of the same data, like in a RAID situation, where you'll have multiple records of the same data. If one has a bad checksum, ZFS will discover that and fix it automatically. So the basic constituent of ZFS is the Z pool. It's what you defined to be used by ZFS. So it's the base unit of storage. See it like an LVM VG, basically. It's the thing that you carve stuff out of it. It's made, you use block devices, but I mean, if you want to try on a test server that doesn't have any free block devices or partitions, you can just create a file with DD and give it to ZFS. We'll just be happy with it. But more generally, it works with disk, files, LV, mirrors, RAID Z is the equivalent ZFS of RAID 5. RAID Z2 is RAID 6. RAID Z3 is, well, there's no RAID 7, but it's multiple redundant parity. From the Z pool, you carve file systems. You can also carve Z volumes. We'll discuss that a bit later. And a server can have multiple Z pools that you can tweak. One Z pool more for random I/O, one Z pool more for sequential, or depending on the type of storage that you are using. So a Z pool can have an S log. ZFS has a log of all the operations it is doing, and an S log is a device dedicated to that log. So normally it's a device that doesn't need to be very large, but must be fast in terms of latency and quite good at endurance. So you look at a RAM drive or an Optane from a device that has a very good endurance. And you can also add to ZFS Z pool a cache device, which is basically an extension of the file cache to a device that has a low latency for reads. So let's cover ZFS file system. So what is a file system? It's basically a profile of settings, a mount point, and it's a snapshotable entity. What you snapshot is a file system. It may look like you can have directories intermixed, but what you can snapshot is a file system. You adapt the settings of each file system for the expected workload. The default are geared more toward sequential I/O. For database, you'll try to be more friendly with random I/O operations. And file system can be nested. Well, that's a very important property that we will use when we snapshot at MySQL and want to have a consistent view, because we'll use more than one file system for MySQL. It's very easy to create a file system out of a snapshot that is called a clone. It's very efficient on storage. There's use case for that. So now I'm already late in my time, so I'm trying to skim a bit fast. So ZVols, those are block devices that you use from ZFS. So they are backed by ZFS. See it as a big file that you basically is a block device. So it's very cool if you, let's say, like on my laptop, I have KVM, I use a lot, and I use ZVols with KVM that are carved from ZFS. Let's, for example, look at the steps required to create a three-node cluster. So first, you create your first ZVol, you start KVM on it, and you manage to have a decent configuration with the basic stuff, basic packages loaded. Then you snapshot that ZVol, you clone the snapshot you created 3 times, and you start 3 VMs using the snapshots. So what's important here is, you see you have the device here that's basically out of ZFS. And since I created, for the sake of the example, let's say my base image, when I installed all the packages, had, let's say, 3 gig in size. Now that I created the 3 snapshots, I'm only still using 3 gig. They will start to use, each new file system will start to use more data as their new stuff being written to the new file systems. But all the things that are still commons with the original snapshot are not duplicated, so it's very efficient storage-wise. ZFS use copy on write, so cow, a lot. So let's see what that means exactly. So it never overwrites data directly. So what it will do, it writes somewhere else, and then change the pointers to the new one. So it's what allows ZFS to be transactional. So, and eventually, there are some blocks that are no longer a reference, and the garbage collector of ZFS will remove that. It makes snapshot almost as easy as recording at what transaction you are currently. So if you start a snapshot at transaction 123, it just has to write, this view is protected up to 123, that's it. So there's nothing else to do for ZFS to record a snapshot. So it's very cheap. And because of that also, it's very easy to clone your reference data from the snapshot based on a transaction ID. And it's very useful for backups, the snapshots. And of course, like I said, it's transactional since it's move elsewhere and just move the record, just change the pointers after. It's very efficient. One of the features of ZFS is the ARC, so the adaptive replacement cache. It's the ZFS file cache. It's rather sophisticated. It's configurable. There's what's specific about ZFS, the cache is compressed, so it stores the data compressed from the cache. So even though you have a 1 gig cache, you may be storing 2-point-something gig easily, especially with a database workload. And it can be layered on disk if you have flash devices that have a low latency for reads. Kernel module. So ZFS is a bit like, if you can literally match a parallel ZFS, InnoDB, ext4, XFS, MyISQL. It's about roughly compatible in terms of analogy. So if you look at the MySQL variables, there are much more InnoDB variables than the ones for MyISQL, and it's the same for ZFS. There's a lot of configuration parameters. In Linux, they will show up in sys module ZFS parameters. It's really a place to look at. There's a lot of things there if you want to learn how ZFS works. As of version 0.7.5, the one that comes with Ubuntu 18.04, what I have on my laptop, there's 169 parameters there that can be adjusted. One good example is ZFS arc max, so it's the maximum size you want the arc to be. ZFS arc meta limit limits the amount of metadata in the arc. The metadata are the non-leaves blocks, so everything that forms the structure of the B tree. ZFS free max blocks, that's something that can bite you if you delete a lot of data. ZFS will aggressively, by default, it's, I think, freeing 1,000 blocks per transaction, so it could slow you down for a while if you deleted like 100 gigs of data. We got that at Slack when we tried. That's the issue. The L2 arc write max, so you may have a good, fast flash device to get to use as an L2 arc, but it may not be very good for writes. You can then throttle the write speed to not impact the read performance. Of course, it will take longer to warm up, but it's a trade-off that you can do. And the ZFS TXG timeout, that's one that I discovered. When you write sequentially, asynchronously, to a file, ZFS is transactional, so it has to decide somewhere, okay, that's enough, I commit and continue to write. So that's the ZFS timeout. I think by default it's 3 seconds, 3 or 5 seconds. So that's the way it works. So now let's talk about in more specific cases of using MySQL with ZFS. So what can we do? First, on the ZFS side, when is it a good case to use ZFS? You need data. So if you have a very small data set, it's probably not a great idea, unless the other reasons listed after that apply. But the first cases is you have a fairly large data set that stresses your storage in terms of capacity. Another good reason, you have challenges with backups. I've been introduced to ZFS a few years ago by a customer that had 300 gig of data split about in half between MySQL and InnoDB, and they were needing to have backups that didn't lock. It was very, very hard. So we ended up with ZFS, and we could do a backup per 5 minutes. So it was very efficient that way. If you want to use compression, better not be in a case where you're already maxing out your CPU. So you need some CPU capacity for the compression. And not I/O bound. In none of the benchmarks I'll be showing you, you'll see that you'll be impressed by ZFS performance. It's more like a freight truck. It can move a lot of stuff. It's efficient at, on a large scale, but it never as fast. And there's some reason about that that I'm trying to understand. And it's more geared towards sequential I/O in some cases, but there's things I think that can be done. I'm still exploring that. One other reason is that if you have flash SSDs and when compressed, the data can fit in the L2 ARC, it could be a very good use case. And if you have an S-Log device and your data is saved on flash devices, you may actually be saving your devices, your flash devices, because most of the writes are going to the S-Log, which is not compressed. And what will go to the flash devices is you have an S-Log device will be compressed. So in that case, you will be writing much less, maybe up to 1/8 of the original write load. So it's quite interesting. So the ZFS configuration for MySQL. What I use is 2 file systems to ease the snapshots and be able to accommodate the different I/O characteristics. So the first one I used is varlib MySQL. I changed my way of doing things. I was using 3 file systems, now just 2. So varlib MySQL is the parent, is the basic one. You configure that one for sequential I/O. So use a record size of 128K. You compress with something like gzip, so compression will be very good. It's a big block that to be compressed. And the other file system will be nested, so it's under varlib MySQL, it will be varlib MySQL data. And in it's not, that's the mount point, but inside MySQL you'll have the pool and there will be 2 pool nested. And this one will be geared more toward random I/O, so a faster record size and probably a faster compressor. SD4 is pretty good actually. You can easily get factor of 3 in terms of compression. And if you can have an L2 ARC, they work great. I'll show some results. And really, if you have a latency requirement, a good S-Log device will work will do marvel. If you're on-premise, I really like the Optane cards. They can endure a lot of writes, and they have a rather low latency compared to other flash devices. So, so for MySQL now, first, since ZFS is transactional, the obvious one is that you don't need the InnoDB double write buffer. But then, what about ODirect? In the past, if you started with ODirect, MySQL, and the OS that didn't support it, it will not start. But now it just put a message in the error log that it tried, failed, and decided to continue without it. So it's not a big deal to have InnoDB flush method that ODirect will just be ignored and back to the OSync default. The InnoDB buffer pool, you'll need to keep some memory for the arc, so don't be too aggressive. Maybe backtrack a bit from your regular settings. We tend to push up to 80%. In that case, with ZFS, go down a bit to give some room for the arc. If you have no L2 arc, and you can target about 0.5% of the active data set size, but that's really not a hard rule. So for 1 terabyte it would be about 5 gigabyte of arc. That's just to make sure the top levels, the nodes of the B trees, not the leaves, at least are in the arc. But if you're really not IO bound, you may not care about that, and it's not a big deal. Again, it's not a hard rule. The data dir, you'll set it to varlib MySQL data so that the InnoDB data files will be stored there. InnoDB log group, home dir, log bin, slow log, relay log, etc. all go to the parent, which is geared towards sequential I/O. In that case, that would be more efficient. So if there's question, do not hesitate, although the time is quickly running by given the difficulties we had. So let's go to some examples. Let's say you want to set up a disaster recovery slave, and here I'll take Google Cloud. Let's set up. So you have a data set of about 700 gigabyte. It's pretty good in terms of compression, 2.5x. You have a decent replication traffic, but all the data set is active because the largest tables have UUID primary key, for example. So they are accessed all over the place. So let's see what it would get, what you would be the requirement here. N1 standard 2, $68 per month, but you need 1 terabyte of SSD disk, which is $175 per month, and for a total of $243. I'm not counting out the network bandwidth, just the basic host and storage. With ZFS, what could you do? Let's say same host, but then you use a local NVMe drive, which is fairly cheap. It's only $30 per month, and it's very fast. And you use then a standard spinner for the streamed bin logs, streams, backups there. So the cost there, even though there's a bit more stuff, it's only $118. So the difference is, it's not big here, but we'll see another example which is bigger. So let's say another guy wants to launch a PXE cluster in AWS. So there's a few options again. Let's assume the data set is 2 terabyte in size. Again, 2.5 of the compression, which is fairly conservative. But you need a lot of IOPS, let's say 20K IOPS. So our first option, we want to use XFS on i3 type instances. So you'll store locally, because it's 2 terabyte and you want some headroom, you'll have to use a 4x large instance. So 3 of these, it's a decent amount of money per month. In other options, you can say, okay, I won't use an i3, I will use a regular R5, and I'll provision 3 terabyte drives with 20K provision IOPS, one for each, but that's very, very expensive. So, and yet another option here is to use ZFS on i3, but since it's compressing data, you don't need a 4x large, a 2x large will do. So that's already much cheaper. And you could use a 2 terabyte SC1, again, to stream the bin logs and take snapshots and serialize them to an external storage to have recovery capabilities. So in that case, ZFS will save you more than $1,000 per month. So now, will ZFS perform well? Let's see some examples I did. So I used Sysbench. It has a TPCC workload emulation. It's not the official TPCC benchmark. It doesn't produce the same results exactly, but it's a very good way to generate load. I used the same N1 standard 2 on GCE with the local ephemeral drive, scale 300, and gives a data set of 200 something gig and 2 threads. So it's a low concurrency type workload. On XFS, I was doing 110 transactions, about 2,000 queries per second, but the data set size was 244 gigabyte, 75% used. LZ4 with ZFS-C, we're down to 69, so it's much lower. A bit less than 2,000 queries per second. So we lost about a bit more than a third. But the data set is now only 100 gig, so 39% used. If we pushed a bit harder, let's use gzip, we're down at nearly half the original workload, the original performance, but the data set is now 85. So there's a trade-off there. Of course, gzip is much slower and it's a heavy read and write load, but now you're using only 26% of the storage. So there's quite a good gain there. So what if we add an L2 arc? So same case, but here I'm using a 500 gig normal disk, so it's spinners. So the latency is very high. We're talking about 8 to 10 milliseconds of latency for an IOP. And there's an ephemeral drive. I didn't use with XFS a solution to cache on the ephemeral drive. I could. I use Bcache or DM cache, but let's say straight, the latency is a killer. So we're down at 3 transactions per second, 87 queries per second, and 285, so nearly half the size, more than half is used. Now with ZFS, LZ4, and an L2 arc, I'm at 29. Even though it's a slow disk, the L2 arc is caching. It was warm, of course, when I did the test. Is caching a lot of the reads. The writes are still rather slow, but the reads are all cached, so it's a big saving. And I'm now doing nearly 10 times the number of queries. So, and the size is much smaller. So, see, there's use cases. It's not always easy to figure out which one is the best solution. Conclusion, so MySQL and ZFS are great together. That's a very easy one. And it's easy to try. I didn't have time in 25 minutes to show you how to install and how to configure it, but it's fairly easy. Once you get past the steps, it's not difficult. And I mean, in my cases, I found it so useful that I'm very addicted. My colleagues can confirm that. Yeah. So, any questions? Yes.
In your experience, is it fair to compress in ZFS more, or from a compression ratio perspective as well as performance? How does ZFS compression compare against like RocksDB?
It's a different use case. So actually, I've done a lot of benchmarks on compression, and I even try RocksDB on ZFS. So because RocksDB compresses the SST file, not the log files. So it still use much less space because of that. And I mean, if your use case matches well what RocksDB can do, it's a very good choice. But in some cases, it's not that good because your data, the way it is organized on disk, may not fit what RocksDB is good at. In that case, a more standard B2-based solution like InnoDB works well. So, but if you, in many use cases, like you said, RocksDB compresses a lot, use Z standard, which could find its way in ZFS rather soon. Yeah. Any other question? Okay, so that's about it.